This topic's on linear differential equations, and specifically those that we're going to solve through the use of an integrating factor. And my little picture of Darth Vader is just to indicate that we're going to force a situation that we already know how to solve, and that situation is the situation of exact equations. Now, we should recognise here that we've got a linear differential equation, dy by dx, and y, and we should also notice that actually there's no function in front of the dy by dx, which is never the case when we've got an exact equation. We would always have some function in front of our dy by dx. So let's force that to be the case. Let's multiply through by currently unknown function f of x, and this will give us the following. Now, if this was an exact equation, we know that we could express the left-hand side here as d by dx of f of x multiplied by y. Now, if we expand this, if we differentiate, we're going to get f of x dy by dx, exactly what we wanted here, and we're going to get f prime of x times by y. So now by comparison we should notice that we want f prime of x to equal f of x p of x. Now we're going to employ a neat little trick here and use integration to find out what our f of x function should be. Because if I integrate this with respect to x, we should recall that the integral of f prime of x over f of x is the logarithm of f of x, and that's going to be equal to the integral of p of x dx. Now, raising to the power e gives me f of x is equal to e to the power of the integral of p of x dx, and this here we call our integrating factor. And this is a pretty big deal, so we want to make a song and dance about it, and probably write it down if we haven't got it written down in our notes. So, let's now go back and look at how we can solve equations using this idea of an integrating factor. So here's our first example. Now, I know this is going to be a question where I'm going to use an integrating factor because I can't split the variables and I haven't got a function in front of my dy by dx. So, just underneath, I'm going to write out my generic equation for questions where I need to use an integrating factor, and compare here that I've got 3 as my p of x function, so that I know p of x is equal to 3. Well, in order to find my integrating factor, I'm going to be interested in the integral of p of x with respect to x, which is the integral of 3 dx, which is 3x. So I know that my integrating factor, my f of x, should be e to the integral of p of x dx, which of course is e to the 3x. Now that I've got that, I can multiply through by my integrating factor and give myself the equation e to the 3x dy by dx plus 3e to the 3x y is equal to e to the 3x times by e to the power of minus 2. Now I know that I've made an exact equation here, and the reason that I know that is because I've multiplied through by my integrating factor, and that was the whole reason for multiplying through by our integrating factor. So my left hand side becomes d by dx of e to the 3x times y, which is equal to, on the left hand side this just becomes e to the x. Now, give myself some more room. Okay, and now all that I'm left to do is to integrate. So we're going to integrate both sides with respect to x, and what we end up with is e to the 3x y being equal to e to the x plus c, which we can obviously rewrite as y equals e to the minus 2x plus c lots of e to the minus 3x. Okay, here's our next example, and of course we're going to run through and do the same thing every time. So underneath I'm just going to write down dy by dx plus p of x y equals q of x. So this time my p of x function is 1, and I'm going to be interested in the integral of p of x dx, which of course would be the integral of 1 dx, which is x. Now, my integrating factor, f of x, will be equal to e to the integral of p of x dx, which is e to the x. Just as an aside note, you might find it interesting to know why we don't add on our constant of integration at this point. Now, if we were to add on a constant of integration, let's think about what would happen here. We would end up with e, our integrating factor, as e to the x plus c. Now another way of writing this would be e to the x times by e to the c, which would be the same as, let's say, another constant a, e to the x, where obviously our e to the c is this constant a. Our step with our integrating factor is to multiply each term of our equation by our integrating factor. Well, if this a is constant, after we've multiplied through by our integrating factor, we could then just divide out the constant a, and that's why I don't need to worry about this plus c at this point. Let's get back to the question in hand, and at this point we're now going to multiply through by our integrating factor, and that is e to the x dy by dx plus e to the xy is equal to x e to the x. Now I know that my left hand side is an exact derivative, and that's of e to the x times by y, and that's going to be equal to x lots of e to the x. Okay, let's just pop that up. Now I can integrate throughout with respect to x, and I can see that here I'm going to have an integration where I'm going to need to do a by parts integration. So I'm going to say u is x, dv is e to the x, so du becomes 1, and v is the integral of e to the x, which is e to the x. U times v minus the integral of v du is going to give me x e to the x minus e to the x plus our constant of integration. And of course the integral of this is just going to be e to the x times by y. And again we can go for one last tidy up and say that y will be equal to x minus 1 plus c e to the minus x. Okay, next question. Bit of a switch. And to our next question. Now, in this question, we are going to solve this by using an integrating factor. Now, in everything that we do with an integrating factor, we never have an argument in front of our dy by dx because we want to put that argument in ourselves. So what we're going to start by doing is just dividing throughout by cosine of x. And if I do so, I am going to end up with dy by dx plus 2, and I'm just going to rearrange this to write this as sine divided by cosine, which gives me tan of x times y is equal to then cosine squared of x. Okay, now this looks like a form that we've seen before, specifically the form of dy by dx plus p of x, y being equal to q of x, and in this case our p of x function is equal to 2 tan of x. So we want to integrate 2 tan x with respect to x, which is going to give us, we can look up in tables, or if we know that cosine differentiates to give us minus sine, then we should know that our answer is going to be minus 2 log of cosine of x. Again, you can slow that down, go through, check it in other places. Now our integrating factor, f of x, will be equal to e to the integral of p of x dx, which of course will be e to the minus 2 log of cosec x. Now it would be nice for us to tidy this up at this point and say that this is e to the log of cosec x to the power of minus 2, because then that we could tidy up even further and say that this was cos x to the power of minus 2. So our integrating factor here becomes 1 over cos squared, or cos to the minus 2. Perhaps we would rather have that written out as 1 over cosine squared. And of course, if we really wanted to, in fact we probably should, write this down as sec squared x, because we know that 1 over cosine is obviously sec. Now going back to my original question, I can multiply through by sec squared and I end up with sec squared x dy by dx plus 2 tan x sec squared x times by y is equal to sec squared x cos squared x. Well, I know that my left hand side is an exact equation because that's how we built it, and that's going to be sec squared x times y. And my left hand side, well, sec squared times cosec squared times cosine squared, becomes 1. And at this point I'm ready to integrate. So let's just move that up a little bit and integrate out so that we end up with the following to give us sec squared x times y, times y is equal to x plus our constant of integration. So y will be equal to x plus c multiplied by cosine squared x. Lovely question. Right, thanks for watching. Make sure you get some practice on that, and all the best.